Your lesson on 4.5 goes over exponential growth, decay. You're going to be looking at different functions, telling whether or not it's an exponential function, and then telling if it is an exponential function, if there's a growth or a decay. You're also going to be graphing these, and then you're also going to be working with word problems that are dealing with growth and decay issues. So if we look at a couple graphs, on the one that you see here on the left, you have a growth because it goes up from left to right. The one on the right, it goes down from left to right, so that one gives you a decay. You can look at these graphs or these function rules, so those formulas, and tell whether or not you have an exponential function. For this first example that you see all the way to the left here, you have x to the third power. Because your power is not your x value, this one is not an exponential function. In order for it to be an exponential function, your x has to be in the exponent. So it has to be the power. So that first one there on the left is not an exponential function. The one to the right of that, the 5 to the power of x, is an exponential function because your x is your power. Your base here is 5, and because that 5 is greater than 1, this shows that this exponential function will have a growth. So it will go up from left to right. To the right of that, you have negative 6 to the second power. This does not even have an x involved in it, so this is not an exponential function. However, the one all the way to the right, you have 0.4 to the power of x. Your x is your power, so it is an exponential function. And your base is 0.4, which is less than 1, greater than 0. So you do have a decay on this function. So with this, we're going to keep this in mind while we graph different functions. So our first one that we have here, we have f of x is equal to 1.5 to the power of x. You're given x values of negative 2, negative 1, 0, 1, and 2. So that's going to give us 1.5 to the power of negative 2. 1.5 to the negative first power, 1.5 to the power of 0, 1.5 to the first, and 1.5 to the second. The two simplest ones to do here is that power of 0, which just means we're going to have 1, and then that power of 1, which means it doesn't change. So it's going to stay the 1.5. If we do the 1.5 to the power of negative 2, that's going to give us 0.4 repeating. So we're going to just round it to 0.4. The 1.5 to the negative first power gives us 0.6 repeating, so we're going to round that to 0.7. And then that 1.5 to the second power gives us 2.25. So these ordered pairs that you're going to be working with here are going to be negative 2, 0.4, negative 1, 0.7, 0, 1, 1, 1.5, and 2, 2.25. So to graph these on your coordinate plane, we have negative 2 at 0.4, which is going to be about here. Then negative 1 at 0.7 is going to be about here. 0, 1 is here. 1, 1.5 is here. And 2 1/4 is here. So you're going to see as you go to the right, your line is going to curve upward. As it goes to the left, it's going to get really close to that x-axis, but it's not going to touch or cross it. By looking just at the graph, you have a growth here because it goes up from left to right. You can also look at your base, which is 1.5. It is greater than 0, or sorry, greater than 1, so there's a growth on this function. For example, B, you have g of x is equal to 30 times 0.8 to the power of x. You're given x values of negative 5, 0, 5, 10, 15, and 20. So we're just going to plug these in first. So we're going to have 30 times 0.8 to the power of negative 5, 30 times 0.8 to the power of 0, 30 times 0.8 to the power of 5, 30 times 0.8 to the power of 10, 30 times 0.8 to the power of 15, and 30 times 0.8 to the power of 20. From here, we're going to use our calculator and just simplify these. For your power of negative 5, that's going to give you a 91.6. The 30 times 0.8 to the power of 0 is just 30. 30 times 0.8 to the power of positive 5 is 9.8. 30 times 0.8 to the power of 10 is 3.2. 30 times 0.8 to the power of 15 is 1.1. And 30 times 0.8 to the power of 20 gives you 0.345, so 0.3. So this gives you ordered pairs of -5, 91.6, 0, 30, 5, 9.8, 10, 3.2, 15, 1.1, and 20, 0.3. On our coordinate plane, first thing we have is that -5, 91.6. That will not fit on our coordinate plane, so we'll move to the next. You have 0, 30, still not on the coordinate plane. The 5, 9.8 is going to be, about here. And then you have your 10, 3.2, which is going to be about here. Your 15, 1.1 is going to be about out here somewhere. So this is going to look like a line similar to this one. Again, you can look at your graph or you can look at the actual function rule. Your function rule has a base of 0.8 where that x is the power 2. It is less than 1, so you have a decay here. You also see that true with the graph or the line that you drew on your coordinate plane. For example C, you have p of x is equal to 5 times 1.2 to the power of x. X values that are given to us are -10, -5, 0, 3, and 5. So the first one we're going to have is 5 times 1.2 to the power of -10. Then 5 times 1.2 to the power of -5, 5 times 1.2 to the power of 0, 5 times 1.2 to the power of 3, and 5 times 1.2 to the 5th power. Again, use your calculator for your power of -10. That gives you 0.8. The 5.12 times to the power of -5 is 2.0. 5 times 1.2 to the power of 0 is just 5. 5 times 1.2 to the 3rd power is 8.6. And 5 times 1.2 to the 5th power is 12.4. So we have ordered pairs here of -10, 0.8, -5, 2.0, 0, 5, 3, 8.6, and 5, 12.4. So on our coordinate plane, when we go to plot these, that -10, 0.8 is going to be about here. Your -5, 2.0 is about here. 0, 5 on your y-axis. Then you have 3, 8.6, which is going to be about here. And the 5, 12.4, you will not be able to put on this coordinate plane. So as we go to the left, we're going to go down and get really close to your x-axis. As we go to the right, we're going to curve upwards. You also see from the given equation that your base is 1.2. That is greater than 1, so you have a growth here. The last part of your lesson goes over using this formula a of t is equal to a times 1 plus or minus r to the power of t. We are going to use this to determine where between what 2 years a value will become either greater than or less than what's given or what's starting. Your a is your initial amount, your r is going to be your rate or your percent as a decimal, and your t is in years. So for the first example that we have, it tells us that Tony purchased a rare 1959 Gibson Les Paul guitar in 2000 for $12,000. That's your initial amount. That's A. It tells you that experts estimate that its value will increase, so it's going up. We'll use the plus sign in the plus or minus by 14% each year. That means your rate is 0.14. It tells you to use a graph. We're not going to be graphing these. We're going to be using the equation and just plugging in values for t, your time, to find where the value will be when it's at 60,000. So we said that there's an increase, which means we're going to use A of t is equal to A times 1 plus r to the power of t. So A, we start at 12,000 times 1 plus 0.14, because that's your rate, to time. I start at 5. Always start at 5. That's just what I do. You can start at whatever number you think is the right one, but this is literally just a guess and check method kind of system that we work here. So if we plug the 5 in to our calculator into this formula, this is going to give us 23,105. We're going to have to go up from here because we're looking for a final value of 60,000. So I would jump to 10. So that's going to give us 12,000 times 1 plus 0.14 to the power of 10. So 12,000 times 1.14 to the power of 10 gives us 44,487. So that's a little bit closer to the 60,000. So I'm going to go up from here, but I'm going to try 12. So 12,000 times 1 plus 0.14 to the power of 12. This gives us 57,815. So that's close to the 60,000. I'm going to go up one more year to see if that 60,000 falls between 12 and 13 years. So that means I have 12,000 times 1 plus 0.14 to the power of 13. And that gives us 65,909. So it is between these 2 years where the 60,000 falls between. So look at the time that you use. You have 12 and 13. So you would just give for your answer between 12 and 13 years. For your next example, it tells you that in 1981, an Australian humpback whale population was at 350 and has increased at a rate of about 14% each year since then. Your A is a 350. Your rate, again, is 0.14, and it's increasing, so we're going to be adding. You want to know between what 2 years the population is predicted to reach 20,000. So this one has a huge jump between 350 to 20,000. So this one, again, we're going to use A of t is equal to A times 1 plus, since we have an increase, R to the power of t. So we're going to start at 350 times 1 plus 0.14 to the power of, I'm going to try 10 on this one, just because I have such a large gap between the 350 and the 20,000. So this would give you 1,298. So again, we're doing a huge jump here, so I'm going to go by 10 again and do 350 times 1 plus 0.14 to the power of 20. See where that gives me. And that gives us 4,810. So again, I'm going to jump another 10 with this because we're going pretty slow here. So we're going to do 350 times 1 plus 0.14 to the power of 30 and see where that gives us. This leaves us with 17,833. So I'm going to try 32 with this, see what that gives me. and that's 23,175. So this is pretty close to 20,000, but I went over it. So I need to go below the 32 and try 31 to see if that's the 2 years that this falls between, because it has to be consecutive years. So we're going to do 350 times 1 plus 0.14 to the power of 31. And that gives us 20,329. So if you look here, that 20,329 is still greater than the 20,000. So we want to go between 30 and 31 years. For our last example, it tells us that the value of a truck bought new for $28,000 decreases by 9.5% each year. So that 28,000 is our A. Our rate is 0.095 because, again, we turn it into a decimal. This one is decreasing, so we're going to use subtraction on this. It tells us to find the value, or find between what 2 years the value will fall to be 5,000. So we're going to use A of t is equal to A times 1 minus r to the power of t. Because, again, this is a decrease, so we're using subtraction. So we're going to start with 28,000 times 1 minus 0.095 to the power of 5. That would give us 16,998. We're going to go up in years on this one, so we're going to jump to 10 also. So it's going to be 28,000 times 1 minus 0.095 to the power of 10. That gives us 10,319. So we're going to go up from here. Also, we're going to try 15 on this one now. So 28,000 times 1 minus 0.095 to the power of 15 gives us 6,265. So we still want to go up on this one. So now we're going to try 16. So with the 16, that gives us 5,669. So we still are not at that 5,000 mark, so we're going to go up one more from the 16 and try 17. So that would give us 5131, which, again, still haven't met the 5,000, so we're going to go up one more year. Try the 18. So it's 28,000 times 1 minus 0.095 to the power of 18. And that gives us 4643. So your 5,000 falls between these. So you look at your time, you have 17 and 18. So you would just say that between 17 and 18 years.